Good morning, physics students. This is Mrs. Krumschreider, and today we are doing the concept development practice page 3-1. And again, you are more than welcome to kind of do this as we do it together, or you can use this just to check your work and check your thoughts. So whatever way works best for you. So this is about distinguishing and making sure you understand the difference between mass and weight. So learning physics is learning the connections among concepts in nature and also learning to distinguish between closely related concepts. Velocity and acceleration, which are treated in the next chapter, are often confused. Similarly, in this chapter, we find that mass and weight are often confused. They aren't the same. Please review the distinction between mass and weight in your textbook. To reinforce your understanding of this distinction, circle the correct answers below. Comparing the concepts of mass and weight, one is basic, fundamental, depending only on the internal makeup of an object and the number and kinds of atoms that compose it. The concept that is fundamental is mass. Okay, so it's mass that is determined by the internal makeup of the object. The concept that additionally depends on location in a gravitational field is weight. Blank is a measure of the amount of matter in an object and only depends on the number and kind of atoms that compose it. That's mass. It can correctly be said that blank is a measure of laziness of an object. Remember, laziness, we're talking about inertia. And mass is a measure of inertia. Blank is related to the gravitational force acting on the object. That's weight. Blank depends on an object's location. It's weight that depends on an object's location. Remember, when I gave you some notes to take, we talked about, or I mentioned the fact that your weight changes on Earth depending upon where you are. So weight depends on an object's location, whereas blank does not. Mass does not. In other words, a stone would have the same blank whether it is on the surface of Earth or on the surface of the moon. It would have the same mass. However, its blank depends on its location, its weight. Okay, so weight on the surface of the Earth and the surface of the moon for the stone would not be the same, but its mass would. On the moon's surface, where gravity is only about 1/6 of Earth gravity, blank of the stone would be the same as on Earth. What stays the same is mass. While mass and weight are not the same, they are blank to each other. They are directly proportional. Remember that directly proportional means that as one goes up, the other goes up. That is not the same as inversely. Inversely proportional means as one goes up, the other goes down. We often kind of represent these with arrows. Directly proportional, we often put like two arrows going the same way. When inversely proportional, we often do arrows going the opposite direction. Okay, so this means if one goes up, the other goes up. You also could do this with if one goes down, the other goes down. Okay, inversely proportional means as one goes up, the other goes down. And mass and weight are directly proportional. In the same location, twice the mass has twice the weight because they're directly proportional. The International System of Units, SI, unit of mass is the kilogram. and the SI unit of force is the Newton. In the United States, it is common to measure the mass of something by measuring its gravitational pull to Earth, its weight. The common unit of weight in the U.S. is the pound. When I step on a weighing scale, two forces act on it, a downward pull of gravity and an upward support force. These equal and opposite forces effectively compress a spring inside the scale that is calibrated to show weight. When in equilibrium, my weight equals mg. So M stands for mass. G is the force of gravity. Okay, really the acceleration due to gravity. So taking a look at the second page of this, where we have some math, so it might be helpful to have a calculator if you're like me and not a super duper strong math student. So, objects with mass also have weight, although they can be weightless under special conditions. If you know the mass of something in kilograms and want its weight in newtons at Earth's surface, you can take advantage of the formula that relates weight and mass. So weight equals mass times the acceleration due to gravity. W equals mg. So the acceleration due to gravity is abbreviated with a g, mass is abbreviated with an m. This is in accord with Newton's second law, written as F equals ma. F, force, equals mass times acceleration. When the force of gravity is the only force, the acceleration of any object of mass m will be g. The acceleration of freefall. Importantly, g acts as a proportionality constant, 10 newtons per kilogram, which is equivalent to 10 meters per second squared. So they gave us some information. So how do we use that information to answer some of these questions? Okay. How much does a 1 kilogram bag of nails weigh on Earth? Weight equals m times g. So m, right, that's this. So we have it here. G is this 10 meters per second squared that they told us right here. Okay. This is also can be g. Okay. So 1 times 10 is 10 meters per second squared, which is 10 newtons. Or simply W equals mg, 1 kilogram times the 10 newtons per kilogram, 10 newtons. So we're probably going to opt to mostly kind of do it this way. Okay? So, answer the following questions. Felicia, the ballet dancer, has a mass of 45 kilograms. What is Felicia's weight in newtons at Earth's surface? So W equals mg. M is 45 kilograms. G is 10 newtons per kilogram. So I'm going to do on my calculator 45 times 10, which gives me 450, and it's going to be newtons. So 450 newtons. Given that 1 kilogram of mass corresponds to 2.2 pounds at Earth's surface, what is Felicia's weight in pounds? Okay, so we know that it's 45 kilograms. And they tell me that 1 kilogram is 2.2 pounds. So I'm going to take 45 and multiply it by 2.2, and so she weighs 99 pounds. What would be Felicia's mass on the surface of Jupiter? The important word here is mass, right? Remember that mass does not change, okay? So her mass would not change. So her mass would still be, okay, the 45 kilograms. What would be Felicia's weight on Jupiter's surface where the acceleration due to gravity is 25 meters per second squared? So W equals mg. The m is 45. But now the g's changed, right? It's not Earth, it's 25 meters per second squared. So again, I need my calculator. 45 times 25 is 1,125 newtons. All right, different masses are hung on a spring scale calibrated in newtons. The force exerted by gravity on 1 kilogram equals 10 newtons. So the force exerted by gravity on 5 kilograms would be 5 times 10, which would be 50 newtons. The force exerted by gravity on blank kilograms is 100 newtons, so I would divide by 10 and get 10 kilograms. Make up your own mass and show the corresponding weight. The force exerted on a gravity of 62.5 kilograms would be 625 newtons. By whatever means, spring scales, measuring balance, etc., find the mass of your physics books, then complete the table. We don't have a way to do that, so we won't worry about that. But let's look at these other ones, right? If my mass is 1 kilogram, then I'm going to multiply that by 10 to figure out my weight, so that's 10 newtons, right? So this, I'm going to multiply by 10 to get that. For my weight, I'm going to take my weight and I'm going to divide it by 10 if I have to get the mass. So 1 newton divided by 10 is 0.1 kilograms. And this last one, 60 kilograms, I'm going to multiply it by 10, so it's 600 newtons. So that wraps up this concept development practice page 2 or 1. I hope that helps with any lingering questions you had about mass and weight. Have a great day. I'll talk to you tomorrow.